Welcome. Today, we're going to dive right into the data detailing how super heavy elements are completely dismantling the classical boundaries of chemistry. For those of us accustomed to the predictable, familiar structure of the periodic table, the information we are about to examine represents a fundamental paradigm shift. We are approaching a frontier where the classical rules simply cease to function. In this explainer, we'll follow a clear path. First, how the periodic law is being challenged. Second, relativistic quantum chemistry. Third, the hunt for unanunium. Fourth, the limits of nuclear synthesis. And finally, the island of stability.
Part 1. The periodic law challenged.
Let's begin with the foundational periodic law. We are well accustomed to classical Splach chemistry. Elements like sodium and calcium exhibit strict +1 or +2 valences, right? Well, recent data from the National Academy of Sciences indicates that the heaviest S-block elements behave radically differently. Elements 87, 88, 119, and 120 can form highly unusual 5 or 6 valent compounds under ambient conditions. The classic periodic law is, quite simply, fundamentally failing at the bottom of the table.
To understand why this structural failure is happening, we have to look at the energetic architecture of the atom itself. The data highlights the core valence energy gap. That's the barrier separating active valence electrons from chemically inactive core shells. For later elements, this gap exceeds 1 Rydberg, which ensures those core shells remain completely inert. Yet, as the data clearly demonstrates, this protective barrier collapses for superheavy elements. Those previously inert noble gas core shells are suddenly available to form chemical bonds.
Part 2. Relativistic quantum chemistry. So why exactly do these core shells become chemically active? To grasp this, we must turn to relativistic quantum mechanics. In extremely heavy atoms, the massive nucleus exerts an immense pull. To avoid collapsing inward, inner electrons have to move at significant fractions of the speed of light. This induces relativistic corrections, specifically the stabilization and contraction of the s and p electron shells. And crucially, these effects scale proportionally to the square of the element's atomic number. The progression is exponential. Consequently, the classical periodic trends we rely on actually reverse. Consider the first ionization energies. Classically, as you move down the alkali metals, ionization energy decreases. Potassium sits at 4.34 electron volts, and cesium drops to 3.89. But the prediction for element 119, unaninium, spikes right back up to 4.53 electron volts. Because of relativistic contraction, that outer 8s electron is pulled incredibly tight to the nucleus, making it exceptionally difficult to remove. Fundamentally, relativity alters the entire electron architecture through strong spin-orbit interactions. These interactions destabilize the outer core p levels while stabilizing the valence s levels. This phenomenon, known as subshell splitting, forces the energy levels of valence and core electrons closer together. In short, it compels those normally inert core electrons to participate in chemistry. Part 3. The hunt for unanenium. This theoretical framework brings us directly to the experimental frontier, the physical synthesis of unanenium, currently the lightest undiscovered element. Positioned as the very first element of a hypothetical 8th period, synthesizing it requires extraordinary global resources. Following the milestone creation of flerovium back in 1998, the RIKEN facility in Japan initiated dedicated campaigns for element 119 in 2018. And looking ahead, major new synthesis experiments are scheduled for 2026 in both Russia and China. Now, physicists rely on highly specific fusion-evaporation methodologies for this. You can't simply smash 2 common elements together. Facilities must bombard incredibly rare heavy actinide targets with accelerated ion beams. For instance, RIKEN utilizes a curium-248 target bombarded by a vanadium-51 beam, while researchers at JINR plan to merge americium-243 with chromium-54. If these massive collaborative engineering efforts succeed, what will the physical reality of this atom actually be? Empirical predictions suggest unanenium will have a highly compressed atomic radius of roughly 240 picometers. To put that into perspective, that is remarkably close to the much lighter element rubidium. This is a very tangible physical consequence of relativistic electron contraction, drawing the entire atom inward. Part 4. Limits of nuclear synthesis. The physical creation of these superheavy atoms is, of course, bounded by severe mechanical and thermodynamic limits. We are quite literally pushing matter to its breaking point. Experimental yields face immense Coulomb repulsion.
Imagine trying to pack an enormous number of positively charged protons into a microscopic space. Furthermore, researchers rely on exceptionally rare target isotopes. And finally, we face dramatically low reaction cross-sections. This means that months of continuous expensive accelerator time might yield only a single viable atom. And even if an atom successfully fuses, its existence is immediately threatened. The highly excited nucleus faces a violent, immediate competition. Primarily, this is between alpha decay, where it expels helium nuclei, and spontaneous fission, where the atom instantly tears itself into two smaller elements. Beta decay also acts constantly to shift the delicate balance of protons and neutrons. The brutal reality of this thermodynamic competition is reflected in unonennium's predicted lifespan. Theoretical calculations suggest the longest-lived alpha decay half-life for the 294 isotope is merely 485 microseconds. If the half-life drops below a single microsecond, the atom will literally decay before it can travel from the target to the detector, rendering it completely invisible to us. Part 5. The Island of Stability. Despite this extreme instability during synthesis, mathematical models point toward a theoretical region that heavily resists rapid, spontaneous fission. We call this the Island of Stability, a predicted set of super-heavy isotopes with considerably longer half-lives. This enhanced survival rate stems from closed magic numbers of protons and neutrons. When an atom hits these magic numbers, its nuclear binding energy reaches a local maximum, creating a structural bulwark against decay. Traditionally, the island of stability was thought to require perfectly spherical nuclei, predicted right around 114 protons and 184 neutrons. However, current literature shows this stabilizing effect also appears in deformed, non-spherical shapes. We observe stability peninsulas located at deformed magic numbers, like 108 protons and 162 neutrons. The island isn't completely isolated. It's actually linked to known stable regions by these deformed structural bridges. If physicists can access the novel reaction channels required to populate the true center of this island, the quantum tunneling projections are absolutely staggering. We're no longer speaking in microseconds here. Copernicium-291 could have a half-life of 100 years. Copernicium-296 could last 1,000 years. Darmstadt-DM-293 might persist for 3,500 years. We are looking at the very real potential for macroscopic, stable quantities of entirely new elements. Which brings us to a profound scientific question. As relativistic effects comprehensively shatter the rules of classical chemistry, what unprecedented states of matter and what entirely novel physical properties await us if we successfully map the center of this stable frontier? We aren't just adding blocks to a table anymore. We are rewriting the textbook on matter itself. I hope this structured analysis has provided you with a clear understanding of the frontiers of super-heavy chemistry. Please like this video and click on the subscribe button and choose notification. Please visit the description for links to resources in this video or from this video, and visit our other channels linked in the description and our websites.